Okay, chemists, today we're going to learn how to read measurements. So you may think you know how to read measurement tools, but there's a specific procedure for it, and we're going to learn how to do that today. So first of all, you need to be reading an actual measurement tool. So Erlenmeyer flask is the one on the left, beaker is the one in the middle, and graduated cylinder is the one on the right. Erlenmeyer flasks and beakers are, even though they have markings, are not measurement tools. So an Erlenmeyer flask and a beaker would be more like a reaction vessel. That's where you're going to actually perform chemical reactions. So you might say to yourself, well, why do they even have milliliter markings on them if we don't use them for measurement? And the reason for that is this is a first-year science course. So I have everything at the lab table ready and waiting for you. But when you get to a real lab course, that's not what's going to happen. You're going to have to go back to stock bottles and get your materials. And the reason these have markings is because you're going to pour an approximate volume in there and then take it back and measure it accurately with your graduated cylinder at your lab test. So you don't want to take 200 milliliters when you only need 50 milliliters, because everything that's taken out of the stock bottle cannot be returned if it's not used. So if you need 50 milliliters, you'll use your beaker to get about 50 milliliters and go back to your lab desk to use your graduated cylinder to measure this. Now, why wouldn't you just take your graduated cylinder, you might be asking, and measure there? The reason is there's not time or space to accurately measure there, first of all. Second of all, we use Erlenmeyer flasks and beakers to transport chemicals because they're cheap. So if you break them, they're cheap to replace. Graduated cylinders are expensive, so you have to be careful that you are using a graduated cylinder very carefully. Now, there's a specific way to read graduated cylinders because of something called a meniscus. A meniscus is the curved top part of the liquid that comes from the fact that water, which is usually what substances are dissolved in, it's a universal solvent, is a polar molecule. So it climbs up the side of the glass. So that's what that curved part is. You would lean down, get yourself at meniscus eye level, and read the bottom of the meniscus. Otherwise, your reading is not going to be accurate. Next, we're going to talk about a concept that we introduced the other day, which is called calibration. Calibration is the smallest marking on the tool. So in order to determine calibration, you subtract two consecutive numbers and divide by the number of spaces between them. So let's look at our first sample measurement tool, which could be a graduated cylinder. You would subtract two numbers, so you've got 20 milliliters marked on there and 15 milliliters marked on there. Subtract those to get 5 milliliters. In between there is also 5 spaces. So each of the markings in each of those spaces is 1 milliliter. If you're on the mark, then you're going to add an estimated digit of 0. If you're somewhere between two marks, you're going to add one estimated digit that tells me how far you think it is between the marks. So you read 18 right off the measurement tool, and I'm saying this is right on the mark, so I'm going to read this as 18.0. So notice the calibration is in the 1 spot. That means your measurement will have a digit in the 10 spot. So if you say 18, that is an incorrect measurement. You need to say 18.0. So if the calibration is in the 1 spot, you will have a digit in your measurement in the 10th spot. Let's look at this graduated cylinder. See if you can calculate the calibration. So I see that two numbers that are written on there are 10 and 5, 15 and 10, 20 and 15. Notice it doesn't matter which two you subtract, you're going to get 5. And then you divide it by the fact that there are 10 spaces in between each number that is written. So the calibration on this particular piece of equipment is 0.5. Each of the lines is worth 0.5 milliliters. So notice my calibration has a digit in the 10th spot. So I'm going to add one extra digit. So I can read 11.5 right off the measurement tool. And then I'll add an estimated digit to have my final reading be 11.50 milliliters. You need to have certain digits read right off the measurement tool, one estimated digit, and then units. Here's a different one. This is a 10 milliliter graduated cylinder, and it's going to have a different calibration. The two numbers written on the graduated cylinder, you subtract them and you get 2. And then there's 10 spaces. So each of the lines is worth 0.2 milliliters. So I would read off the measurement tool, I would read that it is 6.6 because it's 3 lines up and each line is 0.2. And then I'm just going to estimate that it's right on there. So I'm going to report my measurement as 6.60. This measurement tool is a 100 milliliter graduated cylinder, so it has a 1 milliliter calibration. So because my calibration's in the 1 spot, my reading's going to be in the 10 spot. So I can see that everybody's going to agree that the line that the volume goes up to is between 52 and 53 if you look at the bottom of the meniscus. So I'm just going to say I think that measurement is 52.8 milliliters. Now, if you read it as 52.5, 52.7, 52.9, those are also acceptable answers. They're within the range of possible answers. If we were using plastic cylinders, you would not see that meniscus. That's because plastic is a nonpolar molecule and water is polar. So like attracts like, and these guys are not attracting each other. So we're just going to read right at the center. The calibration on this would be 50. That's the difference between 300 and 250 divided by 10. So it's 5 milliliters. So each of the markings is worth 5 milliliters. So that line halfway between is going to be 275. And then you read up 5 for each marking. And I'm going to say my reading on here is 292.5 milliliters. If you thought it was 295 or 293, that's within a range of acceptable answers. Let's pay close attention to these rulers because you are going to be using rulers in the lab. The calibration is 1 divided by 10 or 0.1 centimeters. So my reading has a spot it has a digit in the 100th spot because my calibration has a digit in the 10th spot. So if you think it's right on the line, you can't just say 10.0. You have to say 10.00 centimeters. Remember, all those zeros are significant because they're trailing zeros with a decimal. My next ruler has a calibration of 0.5. It's not as precise of a ruler, it's not as highly calibrated. So you can see that my measurements aren't going to be as exact as the one with more calibration. Now everybody look at this next ruler. We have to be super careful because this ruler has inches on one side and millimeters on the other side. You want to make sure that you're using either millimeters or centimeters or meters. You want to make sure you're using something with the metric system. You do not want to use the inches in science class because otherwise you'll have to convert before we do any calculations. So when we use the bottom, we'll see that the calibration is 1 millimeter. which is also 1/10 of a centimeter. And I will have a reading of 103.5 millimeters. Here's another case of a ruler that is in centimeters. So you have to be careful that you're paying attention to the units that are written on your measurement tool and don't just guess. And don't leave them off because you probably won't be able to remember if you go back. So the calibration on this is 1 centimeter and the reading is 35.0 centimeters. So because I have a calibration in the 1 spot, my reading will have a digit in the 10th spot, which is my estimated digit. The one below is centimeters still, but it has a different calibration of 0.1 centimeter. So my reading is going to have an additional digit in the 100th spot. Thermometers have a typical calibration of 2 degrees Celsius. So you have to be careful that you recognize that each line is worth 2 degrees. So it's 3 lines up. That doesn't make it 33. It makes it 36. And then I'll add an estimated digit of 0.0 because I think it's right on the line. I can also think it's halfway through the line, and this one would have a reading of 62.5 degrees Celsius. Pipettes are going to be measuring how much volume of a liquid is dispensed. So you're really measuring what's missing out of the burette instead of how much liquid the container holds. So in this case, notice that the 21's on top and the 22's on bottom because we're measuring how much is already gone. So my measurement better be between 21 and 22. The calibration in this case is 0.1. So I'm going to read that 21.30 is dispensed. It has to be somewhere between 21 and 22. It has 3 lines missing, so I'm going to say 21.30. We will be using balances tomorrow too. I just need you to be careful when you're reading the mass on a balance that you write all the digits down that are on the balance. There's no calibration marks for you to see, but the instrument is still calibrated. And because there's always a decimal point in there, the trailing zeros are always significant. Leading zeros are not significant, but you need to write down every digit that is on your display. Units will be in grams for our balances. There is a range of correct answers because there is still calibration involved. So it's plus or minus that last digit. So that means that you can have a correct reading somewhere in that range of accuracy. A lot of you are going to come to me and say, oh, the balance, it just keeps going back and forth between 2 numbers. And the reason for that is they're very sensitive balances. So even you talking next to it can change it. But because of the fact that there is a range of correct answers, either one you're going to put down is going to be considered correct. And the difference between our balances that we could use, or rulers that we could use, or graduated cylinders that we could use, is that there is a range of acceptable answers. The more highly calibrated the range of acceptable answers is more narrow, so that gives you a more accurate answer. So the things involved with measurements are accuracy and precision. Accuracy is how close a measurement is to the acceptable value. And precision is how close the measurements are to each other when repeated. So reproducibility is precision, and accuracy is the accepted value or correct value. So those are the 2 different concepts wrapped up in measurement tools. So accuracy and precision can go together. That's what you want. Good accuracy and good precision are correct answers that are repeatable. Poor accuracy but good precision would come from the fact that maybe if you went to the doctor's office and you went to get your weight on a scale, maybe you didn't take your coat off and you had a bunch of coins in the pocket, you're going to get a reproducible weight, but it's not going to be close to the true reading. Poor accuracy and poor precision is when you don't get the same answer over and over again, and they're also not correct. So just a summary, you're going to figure out what your calibration is. You're going to estimate one more additional digit. And then when you report your answer, it's going to have your certain digits plus one estimated digit, and always have units, no naked numbers. Remember these points for when you are in the lab situation.